Hello, this is Jennifer Martinez. This video is on diagonalization of matrices. If you remember from past sections, a diagonal matrix, such as example 1 here, is a square matrix whose entries not on the diagonal are all 0. And the following example illustrates that powers of diagonal matrices are easy to compute. So let's just look at that. So here's D, and if you look at D squared, what is it? So let's just multiply it together and see what you get. And you can see because the first row, first column is just 5 squared, everything else, this is 0 because we have the first row, second column. This one is the second row, first column. That's all 0. And then lastly, we get a 3 squared. So if we take d cubed, that's d times d squared. So if we multiply d and here's d squared, because we just found that, we get a d cubed. So in general, d to the k is just raising the diagonals to the kth power for k bigger or equal to 1. So this is one reason why we would like to diagonalize our matrices. So it turns out that two matrices that are similar can be diagonalized, which is why I want to next talk about the definition of similarity. If A and B are both n by n matrices, then A is similar to B if there is an invertible matrix P such that P inverse times A times P is equal to B. And or equivalently, A equals P, B inverse, P inverse. And by the way, if you have similarity, you can write A, this means similar to B. So first of all, to see these are equivalent. They're equivalent because if you multiply, for instance, both the sides by P on the left, you just always have to make sure you do it on the left, both sides by P. This is a P inverse that doesn't look like it, but this will be an I, so we just have AP equals PB. And then I'm going to multiply both sides by P inverse on the left. We have A is equal to PB, P inverse. So you have it. So we have a note down here, if A is similar to B, then this is equivalent to this, we saw that, but it's also equivalent to this middle step. Sometimes that one's easier to figure out than the inverse, if you don't feel like finding the inverse. AP must be PB. That is the definition of similarity. And it turns out, if A and B are n by n matrices, if they're similar, then they have the same characteristic polynomial and hence the same eigenvalues. Here's the proof of that. Move that up a little bit. All they do here is let A and B are similar, so they wrote B is similar to A by our definition. And then they're going to look at the eigenvalue, B minus lambda I, that part of the characteristic equation. And we are going to substitute the B in for the equation above, and instead of the I, I'm going to write a P inverse times P. Then I'm just going to factor a P inverse on the left and a P on the right. And you can see then they're going to find that characteristic equation, find the determinant of that, which is the same as the determinant we just found. And we know the determinant of A times B is the determinant of A times the determinant of B. These are commutative. So we know these are equal because this is just 1. So they have it. There is 2 warnings. These two matrices are not similar, it turns out, even though they have the same eigenvalues. I know they have the same eigenvalues. They're both 2 because this is a triangular matrix. And the same here. So they both have eigenvalues of 2 with multiplicity 2, but it turns out that they're not similar. We'll come back to this one when we can actually find that P inverse that would make them similar. And the second warning is that similarity is not the same as row equivalence. If A is row equivalent to B, then B equals some EA for some invertible matrix E, and row operations on a matrix usually changes the eigenvalues. So, for instance, on the second one here, if you row reduce that, that would be one diagonal matrix with ones along the diagonal, which is not similar, you'll see, to this one. So now let's go over the definition of diagonalization. Because an n by n matrix A is diagonalizable if there is a diagonal matrix D such that A is similar to D. That is, if there is an invertible n by n matrix P such that PA, P inverse, equals D. Now let's look at example 2. Example 2 says let A be the following matrix. Find a formula for A sub k given that A is equal to P D A inverse. And notice D is a diagonal matrix. And by the way, if A is similar to B, then it could be shown that B is similar to A. So it really doesn't matter where the P and the P inverse goes here. This says that D and A are similar. Let's first check that this does work. So is A indeed P, D, P inverse? So we have P, we have D, oh, we need P inverse. Maybe I could do that over here. And we know the formula for that, that's 1 over the determinant, so -2 minus a -1. -2 minus -1. All, and then we're going to switch those. We switch the A and the D, and then we change the sign to the B and the C. So that should be the inverse. So that's just -1. Just going to change that to this matrix multiplying everything by -1. So there is P inverse. So I'm just going to go ahead and do these two first, though it doesn't matter. So I should get 10 and a 5. The second row, first column should give me a -3. Second row, second column also gives me a -3. So I'm going to multiply these. And you can see it indeed gives A. So again, we have a 10 and a -3. Makes the first row, first column. First row, second column is 5 and -3. And then the second row, first column is -10 and 6 added to 6. And then the last one, second row, second column is -5 added to 6. It works. So that was just a check. What they actually asked us to do is find a formula for A sub k. And it turns out, just as the diagonal matrix was easy to find a formula for, but similar matrices also to a diagonal matrix are also easy to find a formula for. So let's look at that. Let's just start with A squared. And I'm going to use this fact. Oops, that's a P. And you can see if you rearrange this, this is P, D, P inverse, P, and D. My P's and D's are looking alike, P inverse. So this one right here is AD. There we go. This is an I, so what we have is P, D squared, P inverse. Let's do it for A cubed. So I'm going to take A times A squared maybe. So we know the A is P, D, P inverse. A squared we just found was P D squared P inverse. That's a P. Again, the same thing. If you rearrange it, it's going to be P D cubed P inverse. So it looks like my formula for A sub k is going to be P D to the k P inverse. And in example 1, we found what D to the k was. So this is going to be P, the D to the k that we found in example 1, and the P inverse that we found up above. If we multiply that together, we do get the answer for the inverse. And here it is. I took the second two first. I multiplied those, though you could do the other way around. And then I multiplied this first one by this result, and it ended up with some crazy formula. That is the answer. The next thing we're going to do is look at Theorem 5, the diagonalization theorem. This theorem says that an n by n matrix A is diagonalizable if and only if A has n linearly independent vectors. If you're interested in looking at the proof for this, it is in the book on page 284. You can check that out. It turns out that in fact, A, this is similar to a diagonal matrix D, if it's diagonalizable, and if it's equal to P, D, P inverse, with D being the diagonal matrix, that is true if and only if the columns of P are n linearly independent eigenvectors of A. In this case, the diagonal entries of D are the eigenvalues of A that correspond respectively to the eigenvalues of P. So that's interesting. So in other words, A is diagonalizable if and only if there are enough eigenvectors to form a basis for Rn. What does this mean? That means P is going to end up being V1, V2, all the way to Vn, where each Vi is an eigenvector. The columns of P are n linear independent eigenvectors. And D, the diagonal entries of D are the eigenvalues of A that correspond to the eigenvectors in P. So lambda 1 better be the eigenvalue for the eigenvector V1 and so forth. Let's look at an example of this. So now we can find the P and D to diagonalize a matrix. So here's what I'm going to do. Step 1, we're going to find the eigenvalues like we did in the last section. So in this case, if you look at the characteristic equations, we find that the eigenvalues are 5 and negative 2. Step 2, we need to find 2 linearly independent eigenvectors of A, i.e., what we're looking for is the basis for each eigenspace. If you remember, this is the eigenspace. So I'm going to do that. When lambda is 5, I plug in 5 into lambda here, and that's where I get negative 3 and negative 4, and these stay the same. I find the solution to this homogeneous equation, and I get, this is the basis, and I'm just going to let V1 be any vector, so I'm going to let just x1 be 1, and there is V1. I'm going to do the same thing to lambda is negative 2. This is what I got. Plugging in a negative 2 here, we get a 4 and a 3. So the solutions to this are here. And I decided to let x2 be 4, so I didn't have to deal with fractions, but you can do negative 3/4 and 1 if you'd rather. So now we have it. P, we know it's just V1 and V2. So there's a V1 and there's a V2. And D is lambda 1, lambda 2. Just be careful that this is the lambda for the V1, and this would be the lambda for the V2. We found the P and the